please take it away.
Thank you. Thank you for including a statistician in this very CS workshop. And so we're going to talk about work that many people in my group have done and my collaborators. So first, I shall introduce Veridical Data Science, which means truthful data science, a framework we developed the last 10 years. And we have been working very much on the ground with doctors for alignment in medical AI. So AI alignment, if you take the Wikipedia definition, it's really about steer AI system toward a person's or group's intended goals, preferences, and ethical principles. And the AI system is considered aligned if it advances the intended objectives. So for medical AI, who are the humans that we need to align with? They are first doctors whom we work very closely with, and you have patients, and you have administration, right? The hospital needs to make money, and you have public health officials, and you have Medicare, therefore you have taxpayers. And algorithms have been used in medicine most through machine learning, right? This is the project I have been involved with, who decide to give CT scan after injury. When you're in the emergency room, who you can send to for a CT scan with radiation, and who you're going to send to biopsy for prostate cancer. And it's very painful to do biopsy for prostate cancer. And we also work with cardiology from Stanford to decide what experiment to run to find genetic driver for a particular heart disease called hypertrophic cardiomyopathy. It's a heart condition that occurs in 1 in 500 people in the US. But in the future, we're hoping that we can use large language model to help decide treatment for a heart trauma case in emergency department. When things happen very, very fast, there's a case that they might not be familiar with, but maybe the knowledge in the large language models can help make better decisions. And also from the patient's point of view, people are checking already large language models to see whether they have a problem, maybe whether they will go to the emergency room. Now we call doctors and nurses to decide, oh, I don't feel well. Should I go to the emergency room? So all of that need to be maybe enhanced, make it more accessible. And algorithms need to be both predictive and aligned. But alignment in medicine is actually very ancient. It's not a new concept. We don't use the word alignment through medical ethics. Actually, the first code of medical ethics, something called the Formula Committees Architrorum, was first published in the 5th century, was in a German part of the Roman Empire. And the term medical ethics actually came out in 1803. There's an English author and physician, Thomas Percival, published a document describing the requirements and expectations of medical professionals within medical facilities. So the first code of conduct was not about patients, it was about whether they should deepen their knowledge and whether they should consult other physicians. So it's not really patient-facing. And then in 1847, the Code of Ethics, very much relying on Percival's words, were made in medicine. And over the past 100 or more years, people make revisions. And the practice of doctor ethics is part of medical school education, and it's widely accepted in practice throughout the world. So in medical school, usually they emphasize 4 medical ethics principles. Beneficence means you should do good for others. Non-maleficence, cannot do no harm. Autonomy is really respect for persons. And justice is make access equitable. And sprang from the principle of autonomy are informed consent, truth-telling, and confidentiality. Truth-telling by the doctor? Yeah. I don't think this is about the patients. In some sense, you could also ask that maybe we should add that, because if people don't tell the AI the right things, just the doctors, and maybe they bear some responsibility. And in the human subject research, the ethics principles got kind of merged into 3. Instead of called autonomy, it's called respect for persons, and beneficence and non-maleficence got merged, just called beneficence, because it's kind of the same thing, and justice. And there's this famous report in 1979 called Bellman Report. I think it's very interesting. It says that it's from Health and Human Services, three basic principles along those generally accepting a culture tradition. So if you Google on the internet, there was a study about Chinese medicine practice ethics. They don't emphasize as much as autonomy. So that's the culture aspect to the whole medical processes. And you need to respect the culture, and you want to be relevant to the essay research involve human subjects, the principle. So these principles have been implemented in all universities. And let's just look at on the ground, who are these people, these human bodies make this decision to make sure it's alignment, right? All the universities have this RIB called a review board, institutional review board. There's a center at UCSF called Clinical Translational Science Institute. If I talk to my collaborators at UCSF, they will say that if we want this to be used, we need to talk to people in this institute. It's called the Clinical Translational Science Institute. And if you open up their work, you can see the partners, right? You talk to about UCSF researchers, campus partners, affiliates, community partners. This is where the patient component comes in. State partners, public policies, and national partners. Federal has regulations, and consortium partners. This is researcher outside. So this is kind of give you all these people we need to align what they want. I also work with MD Anderson Cancer Center, we call MDACC. They run like over 1,000 clinical trials per year for cancer research, for treatment machines. Some people already start running clinical trials for AI algorithms, but it's very costly, clinical trials. They have 2 institutional review boards, and I asked my colleague there, they said they're talking about maybe merging into one, but they have 2, maybe just too many approvals. And then they have cancer risk committee do the final approval. And then they have data monitoring committee. So the data monitoring committee look at the data. The RRBs are blinded with data. So they try to have some blindness instead of fudging. And FDA require MDC if they worry about the complication or mortality. So you don't always need DMC. See, I don't know, Berkeley has a DMC, but Cancer Research Center, because it's high risk. So they want that. And they don't have decision power. They kind of advisory. And this can make decisions to the next level, and they make the final decision. But statisticians are all these committees. So there's a lot of their work is actually sitting on these committees to approve these proposals. And let's look at the FDA level, federal level. There's a lot of talk we all heard in DC, but so far I can only find April 2024, one documentation, only 4 pages. So run this. First thing is like, what are these things? And you Google, and you find these are the centers under FDA. If you look at the document, it's really agreement of these 4 centers saying, we're going to work together. And we want AI to be safe. So it's very much at the planning stage, not really something on the ground with teeth. If you go back a little further, this is this 2024 documents. So you can see that it's very much high-level principle, let's work together. There's not even detail about, a lot is about money. Half the money for AI regulation going to be distributed among the 4 centers, just nothing like that, because it depends on the federal budget, right? You see, foster collaboration, develop regular approaches, development standards, guidelines, it's all good, but it's very high level. That's where we are at the federal level. Because a lot of times, if you don't have AI researchers there, it's very hard for them to regulate more than this principle everybody can agree with. But bring the 4 centers together, apparently, it's achievement. Yeah, it's called Artificial Intelligence and Medical Products. So it's very much about AI products. If you go back a little further, 2019, there's a small, like 20-page document. There is also about regulatory framework for modifications to AI and machine learning-based software as a medical device. They call it SAMD. this was a discussion paper and request for feedback. I couldn't find a follow-up after they got the feedback, what was decided. So this was in discussion. Well, no, I didn't know they were asking for feedback. But in the document, they do have a flow chart, workflow, which kind of like, let's think about things they care about: data selection, management, data training and tuning, data for retraining, probably deep learning was already in their mind, model validation, performance, clinical evaluation. This is like the alignment aspect, right? They want the clinician to be engaged. Cultural quality, organization excellency, there's human involved here now, probably administration also involved, incentives, there's some alignment there. Review of pre-specifications, probably it's human review. Again, you have alignment issues here. Pre-market assurance of safe, this, I think there's human engaged. Anytime you have human engaged, but there are different groups of human engaged. New live data. They emphasize live data is the data which people just collecting, not something have sitting on the internet for 20 years. And you deploy the models, you have data model monitoring. I think there's human element to that too. You have to take log and track, probably automation and evaluation. And this is just a color, it's about proposed approach. So you can see many of these components will have alignments, but it's not clear who are the people who will make these decisions. But I think these principles actually make sense for general AI, right? I'm not saying it covers everything, but if you think about this, is beneficence, right? You can say AI should benefit the society, do good. Now, maleficence, minimize harm. People already talk. Autonomy, expanded below. Justice, you want equitable access to AI. From the principle of autonomy or respect for persons, authors, I think, should have consent to AI use of their work, which is not happening. Writers, painters, musicians. And ChatGPT can joke about different things, but by scientific fact, I think we should insist should be truth-telling, at least the things we know, right? It's not like everything. And confidentiality is really data privacy. So all these principles, very ancient, general principles, I would say, for AI, not just for medicine. Okay. So come to truthful data science or veridical data science. This has been developed by my group and collaborators for the last 10 years. And the name actually was given by a colleague, Tian Zheng from Columbia. And it's really try to cover part of these principles. It's not everything, but I think it's very much about truth-telling happened, veridical means truthful, beneficence. So try to maximize the benefit. You can go through metrics like sensitivity and specificity metrics. So data science is a pillar of AI. Many advanced AI algorithms rely on data modeling and analysis. So veridical means in veridical data science have two meanings. One is seeking truth. The other is to be truthful about the process, how we seek truth. So that's why we take the process view instead of just modeling. It's important, but other parts could be equally more important. So the paper came out, even my first paper was on stability from 2013, and the PCS framework for veridical data science came out 2020 with my former student, Computability, now at UCSF. It's now have been expanded into a philosophical conceptual framework for practicing data science responsibly with a documentation requirement. It's a framework for producing trustworthy data-driven results and critically assessing trustworthy data result. It's really for scientific reproducibility. Reproducibility for some people means computation reproducibility. That's definitely required, but we want more, the conclusion to hold up, not just about the code can be reproduced. And remember the FDA had a workflow. This is something kind of similar, but we call data science lifecycle. And we have a problem formulation. Usually I want to detect cancer with a high specificity, means true positive rate. And then you have data collection now with genomics. There are many databases. You have UK Biobank, Japan Biobank. For HCM, we started UK Biobank. it's likely that we might find different genes for the Japan Biobank data because they're different ethnic groups, maybe different mechanisms. So there's a lot of selection here, not just collection, meaning now not in the lab, but also going to public databases. And data cleaning is a huge source of uncertainty that prevents us from truth telling. Because two people just change the data differently and we don't usually document about it and forget about it. And we say that, well, okay, now let's do a probability model. And the different analysts, they make different human judgment calls. And do we have the same results, right? And this process view have been written in statistics. And more recently, Gelman-Loken said the garden of forking paths, right? Every step you have choices and you basically have many, many possibilities. So that's what I said, right? Which data from a different database, if you clean the data differently by a different person or different time of the day, you make different choices. And we have so many supervised learning algorithms. You sometimes have different predictions. As a patient, I'll be very disconcerted that you like random forest. You predicted that I should do biopsy. And then somebody said, no, I like lasso. And the lasso says, no, I don't have to. Right? How does we reconcile these differences? And on average, at the population level, they all fit the data pretty well. But for individual medical decisions, they give you different predictions. So motivating for Veridical Data Science, as I said, happened 10 years ago. Got my attention, many other people's attention. There's two papers from industry. One is from Amgen, one is Bayer Healthcare. It's in oncology. And they try to replicate a lot of these landmark discoveries more from research entities. They could only replicate around 11 to 20%. So these major discoveries are not reproducible. And still, I know for a fact that in some cancer center, validation center, the replication rate for biomarkers still less than 10%. So as far as I know that still going. So this Veridical Data Science is a response to the reproducibility crisis. And just 2 years ago, 73 teams of social scientists, they were vetted. So it's now work on the same data set, no worry about data cleaning, for the same prominent social science hypothesis about whether immigration have a positive or negative effects on like social policy support. And they got results from the very negative to the very positive. So this is the same data, same hypothesis, and the organizer vetted. It's not like Kaggle, anybody can do it. They vetted the teams, so they're qualified. And they have title, Hidden Universe Uncertainty. This uncertainty really prevents us from truth telling. So how do we practice Veridical Data Science for alignment in medical AI? This is very much to try to bring statistics and machine learning back together. Follow up on Leo Bryman's 1-2 culture paper, make it one culture. So predictability is a minimum reality check. We have expanded to many other ways too, but at least you should do some predictability on test set. And computability, very much center machine learning, so we take that, but we add data-inspired simulations. And then stability is a huge expansion of statistical sample-to-sample variability to relevant perturbation from data choice, data cleaning, human judgment calls. And we really want to unify and synthesize and expand on idea-based practices from machine learning and statistical reliable, responsible data science. So I kind of embark on this journey to really liking stability principle about 10 years ago. I think it's very fundamental. There I wrote 2013. At the minimum, reproducibility manifests itself in the stability of statistical result related to reasonable perturbation to data to the method or model use. There, I was not thinking about whole pipeline. I was thinking about modeling. I tried to marry the perturbation sample to Tukey's robust statistics model perturbation. But I didn't use robust statistics because it's become quite specified or quite narrow. And by 2020, we already expanded the stability principle and also the reality check principle to the whole data science pipeline. Every step you knew about reality check and stability. There's already linguistic stability, right? When we have multidisciplinary people, when I was a graduate student, ML was maximum likelihood. right? That's 30 years ago. Right now, it's machine learning, right? So the terminology, even in statistics, people say ML. It's not maximum likelihood anymore. So with multiple discipline people, you have linguistic stability. People have to agree on that the word means the same thing. And consider the perturbation above, but also can include numerical stability and data augmentation and stability from control theory. So it's really trying to build a big tent. All these different perturbations. Science is about perturbation, right? You don't do something, you see what happens. So perturbation is very fundamental. And also on the theory side, if you look at statistics, at least the IID literature, central limit theorem and concentration result are all stability result, right? There's a proof of central limit theorem called the Lindenberg swapping trick. You just swap in random variables one by one with the same mean, with the Gaussian, all of that, you prove central limit theorem. And random matrices, right? You look at the proof, it's very much a perturbation argument. And from machine learning, there's uniform stability and recent work, just the last couple of years, people are returning to stability. But stability is such a broad concept, so it's very flexible for us to use to formulate in a way that solve the problem. It's not one thing. On the ground, my team has been working on using these principles for finding, we found 2 epistacy drivers for HCM, and we hope one day there'll be a drug. And we also simplified the process tensor scoring system from 18 genes to 8 genes, and now we're part of patent application and disclosure of that. And also we're finishing a paper or sending a paper to use these ideas to come up with synthetic stories to probe the human brain to understand which part of the brain care about which type of emotions and things like that. So it's really cross different fields. We have seen a lot of success in using these principles. And documentation is such a big part. How do you know it's reasonable? The context decides it. So you have to document it and make a case about what's reasonable. And you should have narratives and code and quantitative, qualitative arguments in a piece of documentation. And we have a template at my website. You can kind of just lift it and put into your problems and do it. Especially for beginners, very, very helpful. So if you look at this machine learning workflow from the 2019 FDA document, right, you can easily see that, well, I mentioned about data cleaning, that's data management. I'm advocating you keep 2 copies of clean data if you can afford it, and just run the pipeline. Get very different results, you're in trouble, right? You have to go back, either say one is not the right way, write a document about it, or you find stabilize it, the whole pipeline. And here's another one, model monitoring, evaluate performance. You should use multiple metrics. It's not just multiple models. You should use metrics, not just L2, maybe L1, maybe relative error. So there you want stability analysis. So you can see these ideas can be integrated into this workflow. Alignment deals with humans, so it has to be interpreted to humans. So that's why interval machine learning becomes very important. And we don't really know when you give me a black box. Are these decision rules follow the 4 medical principles? And if the model is very unstable, you don't want to interpret it because you're just interpreting noise. So these are all prerequisites. And for medical purposes, people care about sensitivity, which is a true positive rate. People have the disease, you want to find them as much as possible. But then there's a trade-off, which is the specificity, which is a true negative rate. You also want high true negative rate. So when you tune some threshold, usually you have to trade this off. And sometimes you don't want to do a cut. People look at the area under the curve. That's kind of an average. Usually it seems pretty like monotony increasing. So if your AUC is better, usually anytime you cut, usually that's better too. All the curves I have seen have that kind of like upper bound type of phenomenon. So it doesn't have usually the weird things that you have good AUC, but particular sensitivity is really bad. So that's why AUC has been one number. And autonomy, right? So you need to be truthful to the process, to your data, and informed consent, and differential privacy actually is a form of stability. And fairness is also a form of stability. So this kind of nicely intersect with these medical ethics principles. So let's look at what's going on the ground with AI and medicine. So I was surprised. I was at the Machine Learning for Healthcare conference in Toronto in August. I was actually shocked. Unity Health in Toronto are implementing many AI algorithms. I said, don't you need approval? And they said, well, if you only do it in one hospital, it can be done under quality improvement. Just they make decisions. So in theory, UCSF could also do that with this translational clinic. And they are allowed to use this PCON. It's a pediatric ER doctor kind of network. They have rules, and we work with them. And they said they just, in the emergency room, they just pull out that and use it. It's not exactly approved, but it's approved by this group of doctors, so there's some authority there. But here, they just implement it, and they seem to be a pretty good team and very sensible. But if the algorithm needs to be used by other hospitals, FDA approval is needed. So that's why, but FDA doesn't really have very clear regulation yet. Okay, so the next part I'll talk about our collaborations with people at different places. So I talked to a colleague from MD Anderson Cancer Center, and she said, I'm visiting them in 2 weeks. Clinicians at MD Anderson are still very skeptical about AI. So that's why I think we need AI researchers need to have close collaborations, right? There are many attempts from the tech industry, like Google Health, all of that, haven't made the inroads. Mostly, I think it's lacking of this close collaboration. So for the rest of the talk is our work. I will showcase 4 case studies, all working with clinicians at UCSF, and to show that how we bring in this alignment or how we make things aligned. The first is decision rules, which is human can look at, so it's very aligned. And the second is going to large language models. We're building pipelines of interpretation, so to help the doctor to probe the large language models to see whether it's aligned with their intentions or medical knowledge. And then we also look into some cost, which very concern the administration. And I'll end with some challenges and current directions. So why we like clinical decision rules, CDRs? Because people can look at it and they say, yes, this captures what I understand about. It's really medical reasoning. It's kind of the old AI rules, right? But data-driven, and they look at them. And they're commonly used in clinical settings. So we have been working on this for the last couple of years. And in emergency room, it's very high stake, things move very fast. So these rules are very, very helpful. And they tell them how decision made, and they are the gold standard. This is the team people I've worked with over the years from my group, and this is a doctor from ER department in UCSF, and AD's here. And this is something quite cute. And my former student, Chandon Joe, right, about this collaboration. We stress tested their CDR. This is already in place. We redid analysis, follow the stability and all of that, and they passed. We also have external study. So this is the PCON rules, right? Abdominal trauma, some kids show up in your emergency room. GCS score is some kind of cognitive score. If you're not really awake, you're in trouble, and you have all these symptoms. And here decide whether you should go to CT scan or not. So this is a decision. And we redid everything, and they came out really well because this is a pretty good team. We had external study. Part of it is actually have the 2 teams, have 2 studies, agree on what this variable means. It's kind of human alliance. They don't use exactly the same variable. But we want to improve decision trees. So we end up working on fast interval greedy trees called FIX. We had an early paper, Abby was part of, showed that if you have additive functions, trees cannot capture that. There's some theoretical result you can show that it doesn't give you the optimal results. So we said, well, maybe we should do additive trees. So we designed this. You control the number of splits, but you do addition of trees in a sequential manner. So this is a cart, right? You start and you split and so on and so forth. How does fix differ? First is the same. The second, you already have a split. You decide, should I split more or should I add a node? So that's always, you control how many total. So it's complexity controlled. You just use residual to refit, and so on and so forth. And then if you use that, this is the P-CARM existing decision rule. If you look at 94% sensitivity, which means 94% people really need CT scan, also have internal bleeding, are detected. And you look at the specificity. So we really lift the specificity quite big, right? This is 9%, this is doubled. And this is 5 more times. And this is almost not quite doubled, a little bit. So you can see that we really lift the true negatives, which means that fewer kids are sent to CT because of radiation. So it's quite a big. If you go to 98%, actually here, the P-CARM is like 1 point something, here we got to 16. So it's even huge lift of true detection, negative detection rate. And now we do a lot of PCI scrutiny, right? We do stability analysis. So this is a particular one you look at. And we have decision trees. So this is the first, the second, and third. And you look at them, actually make a lot of sense. The first top tree is about sign of injury. The second one is about mode of arrival. And the third is severity of injury. So naturally, this entangles the different reasons for some injury, which you won't see if you have only one decision tree. And we did a lot of perturbation analysis stability to make sure this is stable, not just because we change data by 10%, the whole story change. So that's why it's a necessity. And now moving to the large language models. So we want to interpret to help people to understand what does it do. So Aliyah is here, who is the lead on all this project. And people have used large language model for many medical data sets. But there's concern about safety and are they aligned with human intentions? So we need to interpret because they cannot look at the code and understand. Unlike decision trees, they can, and they can interpret themselves if you just present it the way I presented. So this is the first peek into the black box. It was an ACLA paper this year. We call SUFO, supervised probing and supervised similarity analysis, future outline analysis. So it's multiple steps. With a urology from UCSF. This is from Microsoft, and Yosha used to be here, and Britain was a former student, and Leah is right there, the lead also. So this work started a long time ago because we had to work with the doctor. So we're using now the most recent large language models about the bird family. And the task is to look at prostate cancer report and try to extract the primary Gleason score. That's the cancer grade score for prostate cancer. It's called Gleason score. Can we extract that from the medical pathology report? So a pipeline finds that the feature space, which is the last layer, actually goes significant specification after fine-tuning. So we start with this public bird-like, it's about 100 million parameters models, public models, and we fine-tune our pathology report, which you cannot leave UCSF had to be done there. So there's very interesting specification. So it really enables us to detect outliers. And we talk to the doctor, and this is a pipeline in the interest time of say just multiple steps. And we talked to the doctor, and they said, what are the hard cases for this Gleason score? They said sometimes just wrongly labeled, sometimes inconsistent. Sometimes you have multiple source information, they get confused. Sometimes just got truncated, didn't get reported. And there's something just on the borderline, right? So this is from human. And we want to see whether we can find a way to identify this automatically. And we're able to do that. And it turns out that if you have mixed domain training data before you fine tune, it's the most aligned with the human intention in terms of finding these hard cases. And I think we can help improve alignment by giving feedback. We haven't done that. Maybe we can put a stop saying if this is detected as outliers, we just don't give output, just say clinicians should take a look. So that will really increase the truth telling and accuracy. So the second project is under review. It's really expanding contextual decomposition from transformers. And these are two doctors, urologists, and Yaxuan is also here, and undergrad Georgia and Joshua. Joshua now is in Harvard. So this is about mechanistic circuits, right? People start with marginal, like Lime, IG, and Sharp. We did our contextual decomposition for future interactions. Now we look at subnetworks to try to interpret a particular prediction. That's called mechanistic interpretation, started by Anthropic. So we took our contextual decomposition, which was done by Murdoch and Chandon Singh in the group, and we extended for transformers. And with non-trivial coding work, that's what Aliyah led, to really say that, we identify circuits of attention heads in, again, bird-like models, and to see what are the responsible. And we take a look at the circuits identified, we evaluate it, and we basically give a different angle to these large models than what we previously developed. So it's actually, we have quite a bit of mathematical equations. That was the design, and try to make that computable efficiently. It's non-trivial. We're able to identify phase-fold circuits, and we did a PCS stability analysis to make sure that we're not just seeing something because there's a random starting, how we started the fine-tuning, and how we did the ablation, how did the corruption ablation. So this is compared with 3 data sets people usually use with 2 other methods. The blues are methods, the different sign shapes are different data sets. We can see that we're quite up there. For this one, it's EAP. It's a particular activation attribution method through path patching, kind of comparable. This is time, running time in log second, and this is the AUC as a benchmark for medical that matters. So we're pretty doing well. When there's also something called faithfulness, you compare with random circuits, and then see whether you do well. We do pretty well compared with random circuits. And now the circuits can be backtracked back to the input and find the words. And you do the word embeddings and you do PCs and see what they are. Because we do this circuit, we do layer by layer, and you can see all of them. You can inspect. They all make sense. And then we did also some random circuits. You don't see something like that. It just seems to be pretty much random. So we find medical terms related to prostate cancer and helpful words, and also punctuation numbers. These allow more detailed alignment assessment than the previous work we did. Yeah.
The details, but okay, so you found these words that come up.
Yeah.
Which don't come up in random circuits.
Yeah.
But how does that tell you anything about alignment?
Because you want this to be medical related. This is trying to explain how the model identify to give the Gleason score. So this is trying to make the inner working of the prediction, which is a bird model, more like half transparent.
I understand that it gives you a peak.
Yeah.
But a peak does not.
But if you something say it's not medical, you might want to change that to suppress that and make it more aligned. Right. Because this makes sense. That's good.
Well, this is good.
Yeah.
It's better than he's thinking about medical things than it didn't think about medical things.
Right.
But is it thinking about it in the right way, or the way that you define to be aligned?
So you're saying that we can use a different method to do interpretation. That's what we haven't done that. We did a little bit of that with the other methods.
What do you do with that?
What?
Okay, so you found out that these words were relevant, right?
This is more give, say, Annabelle. He might just feel more confident, hopefully, to use it in his clinical. Right. So this could be part of the assessment process. So we have earlier versions of machine learning to do the extraction. It's already sitting at the common data at UCSF, people using it, but we haven't deployed this. Because this could be used for all the doctors to do research to extract the Gleason score from the pathology report. And this is something, could be, say, people sitting on the Translational Institute look at it, say, okay, now I think we feel safe to deploy this in the platform. It's the grade, the cancer grade. So we have this pathology report in the narrative form, but people want to do something, they want the structured data. So humans can extract that, but want to automate that. And if you keep making errors, then that's a problem. So we want that step to be vetted. And we had a simpler method, use logistic regression is being used, but this hasn't been used. And I think this probably gives better accuracy than the previous one. But because it's not as transparent, or not as line, we haven't approached them to say that, hey, why don't you replace our previous algorithms, use logistic regression by this one. So this process is facilitating that. Maybe they say, oh, now it's going to be the Translational Institute, or somebody makes this decision, at least people at the Berkeley Institute will have to make that decision. They took the logistic regression type of work from us, but they haven't done that. So now everybody's using that to attract from other cancer, from all the new prostate cancer reports, right? We worked for 5 years ago, right? So all the new reports, yes, yeah. Okay, so the last one, go very quickly, is that we basically produce an AI system that to reduce crowding and cost for the ER, and that use some reinforcement learning, and this is still research, whether they will adapt that. I think we try to duplicate now. This is use mimic data, and we try to replicate it right now with the UCSF data. Okay, so this is the last part. I should say that we wrote a small paper with my colleague here about, if you look at Veridical Data Science for medical foundation models, the whole data science life cycle changed, right? There's upstream, completely a black box. We don't know what's data. We don't know how decisions are made, what the algorithms used, and downstream is more transparent. So you look at all the three principal PCS, I think we need more better benchmark data for medicine. That's what we try to build on. And we need to do more perturbations. All of this, we need collaboration. Maybe some academic team can work with industry if they want to be completely open. And then how to do the prompt engineering, all of that. Basically, we need to do a lot of stability analysis and reality check. And it's a good thing that NSF now have some resources for to use, but still very limited. And FDA-like procedures maybe should be implemented, but depends on FDA whether they want to go there. So what we're doing now is we're building a data set, scraping from ED exams, so to facilitate truth telling. And we're going to bring the human understandable decision rule together with large language models to constrain, to bring the reasoning into the large language models for truth telling. And we might improve our CDT, and we're working on uncertainty quantification. So the book just came out yesterday, actually, and it's free versions there since February. And if you want to use it to go with a mathematical book, that's what I do for upper division, beginning graduate, and domain expert. Thank you.
Any questions?
What's the question? Yeah.
Yeah, I had a question. I guess, thanks for a really cool talk. Back to the, I guess, the interpretability point, right, where you find these features that seem to correlate with the relevant medical terms, right?
Yeah.
It strikes me that they're kind of like, and you call that an alignment assessment. And it strikes me like at least two reasons why you might want to do that. One of them is that if you have additional confidence to believe that the algorithm is paying attention to the right features, then it ought to generalize better in the right ways beyond the training set. Because one worry is that I just picked up these like spurious correlations, right? I think and that's one reason why you can use that for alignment assessment, right? You have to you believe it will affect downstream performance somehow.
Yeah, that's one thing. We can get newer data to see actually have that. That's a very good idea. Yeah. We haven't done that. We've been working with the same data, I suppose, just to kind of change the toolbox. Yeah.
I think the other thing that came to mind is like sometimes in some medical applications, maybe you shouldn't pay attention to certain features because you believe for ethical reasons that you shouldn't condition on certain kinds of data. I'm thinking of sometimes you may not want to condition on race or various kinds of things like that. And if I'm curious if it seems like this kind of thing could let you kind of detect whether it's paying attention to terms it shouldn't and scrub that out or something like that. Yeah.
Yeah, definitely it happens. That's why I usually want to look at multiple methods. We have been pretty busy doing our math, in cancer research stuff. We actually look at multiple methods, and for all the good models, want them to gray before I integrate it. But here we just haven't had the manpower to really run a lot of things. But that's what the next step. I think before, hopefully they're gonna look at this, put it on the data commons and use that. This kind of form, I'll call like form of stability analysis, look at analysis. I'm very plural. I want to see multiple approaches, but you want to vet them so that they're all good methods. And so one difference between this and SHAP is that SHAP just can be built on any models. This is really taking into account all the weights and the paths. Just very intimately taking information after the deployment. And then therefore it's faster. You don't have to feed like outlier. Yeah. That's for all the comments.
We have a question is on this, like comments on the stability. Suppose your model kind of, all model are kind of, your class of model you try, right, in this kind of BBS framework, you do kind of manipulating the data to judge whether it's stable or not. But if, just, have you ever given a thought, if your model actually, all the models are kind of biased, they kind of consistent with each other, but not necessarily reflect the truth. So do you have anything to protect against that?
Well, bias usually you need something to calibrate against. Right? If you introduce external source information, you can protect. So that I would say that that's a form of perturbation. You perturb in the right way, like transfer learning or something. We haven't done that, but the bias is a tricky issue because you need something to calibrate against.
Right.
Without the information, there's no way to. Yeah. So reality check through the doctor, but the doctor can all be wrong, but that's where we are.
Right.
Right. So we can never get complete, like we used to think the earth is flat, right? So there's nothing until somebody says not, and then we look at it. So that's a fundamental difficulty, I think, for all data-driven results. But the critical thinking hopefully help you to think harder. Yeah.
So I think it was over a year ago when Pam Samuelson gave a talk about copyright. She spoke about the fact that maybe eventually the laws that will govern LLMs will be derived from other laws. So laws that have to do with copyright, for example, and rather than directly. So similarly, there are all kinds of laws that have to do with medical treatment, I guess. Laws, yeah. So that could also, if you're using AI for that purpose and they violate those laws, it might be another indirect way to put regulations on AI models.
That's what I thought.
Other downstream effects, yeah.
And that's what I thought FDA would be doing, because they're so used to regulating the traditional treatments, right? They're still taking them very long to come with anything more concrete. Because it's also because AI is just happening so fast.
So you need somebody to sue. So just like with the copyright, right? There were these actresses that were suing, so you need somebody who got medically
So
maltreated.
we want somebody to sue AI algorithms.
I don't know if you want to, but that's probably going to happen.
But I think people have to understand the AI algorithm to sue. So that makes the bar sometimes so high. Yeah. I'm sure there might be some lawsuits we don't know about.
The FDA regulation with respect to features or how these models are used in a data science context, I can sort of envision how that could work downstream, but have you seen or heard any discussion on regulation of, let's say, an AI therapist where it's all language, basically, what happens?
No, I haven't seen anything on that. That's not people too worried, I guess. It's more, I think the interaction of patients and doctor with large language models. I know both Stanford and UCSF have the ChatGPT versions available, but it's only for research.
I see.
But I was surprised Unity Health in Canada, they seem to be a lot more advanced in using it. So I think it's very uneven right now. I talked to Aaron, he said, oh, I'm on this governance committee, I'm on that committee. But it seems that UCSF is organizing these committees. At least I think in theory, nobody can stop them from using it, but they have to take the legal responsibilities. The human sense is probably preventing them from using it. But Pecan, right, I was just surprised. They pull out the cell phone and they look at it and they use it. But it's very simple. I was surprised that was not FDA approved. It's just Pecan put it out. It's like hundreds of pediatrician doctors and they just use it. So for their purpose, they actually try to transfer knowledge for non-pediatric ER doctors. Because many kids are treated by people without pediatric training, so that's their purpose, to transfer their knowledge to the people who are not experienced with kids. And they just did it.
Yeah. Relevant for some of us with kids who go to the ER. So let's thank Ben again. And we've got
Yep. Thank you.